Welcome to our webcast, The Importance of Demagnetizing Transformer Cores. Today we'll be talking about what causes transformer core saturation, how this affects transformer performance, and some best practices for demagnetizing transformers in the field. My name is Yerto. I'm the Marketing Communications Engineer for Mega North America, and I'll be acting as the moderator for today's presentation. If you have any technical issues or questions for our presenter during the session, I will be supporting you. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit the questions at any time during the presentation by typing in the box highlighted in red. You may also notice that there are two audio options, telephone and mic and speakers. The mic and speakers options uses voice over IP, so you may experience intermittent audio lag due to bandwidth. At any time during the presentation, you can switch to the telephone audio option. You will receive a copy of the presentation afterwards, and remember, you can ask questions at any time during the presentation, and I will interject your questions as we have time. Our presenter today is Dr. Diego Robinino, Mega's Senior Applications Engineer. Diego is based out of Dallas, Texas. Thank you for joining us, Diego.
Good morning, everyone. Ladies and gentlemen, it's a pleasure to have you here and attending to this webinar. Today we're going to talk about one of the problems that we're facing in the field, which is transformer demagnetization. Many people have asked the question, well, what is the problem about having the core magnetized? Will it affect any operational condition? Will it affect any testing condition? So we will go step by step, understanding first what is the physical phenomena. As you can see in this outline, we will go through the transformer core saturation first, the effects of saturation. We will talk a little bit about the Inrush Current effect. We will go into more detail when we talk about the effect of testing procedures. And then we will show you a few demagnetization processes that are being analyzed in this presentation. For every presentation, we should have a motivation. And many of you are buying power transformers for your substations, and you are investing maybe $500,000, maybe $3 million, maybe any other number. And the big question is, how long do I have to operate this unit? The investment that I'm doing today is good for how long? So we really need to understand that the idea of having this transformer is to provide continuous, reliable, and safe operation throughout the service life of this transformer. So how can we get this done? We have some important questions to answer here. If we're looking at our transformer as an investment, do I need to do anything with this transformer? If I have to do anything, then what should I do? And okay, so why am I doing it? What are the consequences of doing it or maybe not doing it? So we need to understand all these processes, and especially if you are an asset manager and you have to take decisions about the operation, maintenance, or just removing from operation one of these units. Let's understand, why are we doing this? What has to be done in our system to improve the quality, to improve the service, to improve the reliability of our units. So let's talk first about the transformer saturation. We will see here the electromagnetic phenomena. And let's start from the ideal transformer. When we're talking about the ideal transformer, we are talking about something just so beautiful and wonderful that there are no losses, right? And the ideal transformer is based on two principles. The first one, a variable electrical current produces a variable magnetic field, okay? And this variable magnetic field produces a voltage across the ends of the coil. So as you can see here in this simple example, we have an excitation voltage that is being applied to a coil. Now, it's creating this electric current, a magnetic field, and you can see the flow of the flux, right? Through the pad, in this case, the pad is the magnetic core of the transformer, which has something specific for that material, which is the permeability of the core. When we're looking at the physical phenomena, we need to understand the laws ruling this process. So the first one, the electromagnetic induction, is the Faraday's law. What is it telling us? That basically, when we're applying this voltage, right, we have a change of rate of the flux with respect to time. But if we have uniform flux, the distribution here will be related to the flux density and the cross-section of the core, as you can see here. Now, we need to understand that it's not only one term what we are applying, but it's several terms that we have in the core. So basically, the relation that we have for the electromagnetic induction is as shown on the last equation here. Let's understand Lenz's law, because here we're saying that the voltage that is being induced by the changing flux is of the polarity that tends to drive a current through the loop to counteract the flux change. What is it trying to tell us? That basically we have a changing flux induces a voltage as a function of time. But this voltage, right, if we divide this voltage to the impedance of the system, we basically have a current as a function of time. And this current that is now being created is also inducing a flux, this P prime of T, which is opposed in direction to the changes in the flux originally generated as a function of time. And now we have to look into the physical phenomena here. And we look at the Ampere's law. And we see that the net magnetomotive force around a closed path is equal to the total current passing through the interior of the path. You can clearly see here that we're defining the field, right? And we're defining the magnetic path length in the core to analyze this and to apply into our equation for the uniform magnetic field strength and the number of turns. Let's put all these laws together and let's try to correlate them. We have an excitation voltage. We look at the Faraday's law, and we are correlating this excitation voltage with the flux and the flux density. From here, we're looking at the core characteristics, and we can correlate flux density with the strength of the field and the force. Same way, we correlate now using Ampere's law, the strength of the field with the current, and if we look just at terminal characteristics, we're thinking basically Ohm's law, correlating current and voltage. So everything is correlated in this system. Let's look now into the construction itself. What are we having here? What are we dealing with right now? We're looking at electrical steel, which in reality is low carbon content iron silicon alloys. And these flat rolled magnetic materials, in which silicon is the principal alloying element, these are the ones that are being used, and those have some specific electrical and magnetic characteristics that make those suitable for laminated cores in power and distribution transformers. Now, we have to remember that these magnetic materials, right, are not only used for transformers. So let's look a little bit more about this. And one of the things that I want you guys to remember is that there are several classes of electrical steels and grades. And when you are selecting, when you are preparing a bid process, and you are defining the characteristics and the efficiency of your transformer, one of the key points to put a little bit more of attention when you're preparing this technical package is, of course, the core characteristics. As a reference, you can look into the American Iron and Steel Institute, AISI, and they have assigned a type number to each grade according to its core laws. So, of course, if you're looking for a cheap core, there will be more losses. If you're willing to pay more and have a more efficient system, then you're looking for less losses in the core. There's several improved manufacturing techniques like building with two lamination packets, step lock joints, V-notch laminations, boltless cores, etc. So here we go. And now we can talk about non-oriented electrical steels, NOES, right? In this case, the magnetic properties are practically the same in any direction of magnetization in the plane of the material. What I'm saying here is that the system itself has any direction. It has not been oriented by any process during manufacture. And you can see on the right-hand side of your screen, this non-oriented grade, according to the designation of the AISI, you have M15, M19, M22, 27, 36, 43, 45, 47. The higher the number, the higher the losses. If you go on the grain-oriented electrical steels, now here, these alloys are suitable, produced with a metallic crystal structure in which the grains are aligned so that magnetic properties are vastly superior in the direction of rolling. And here you will see especially one of the typical material we use for transform are in this area on the M3. So you need to decide that with the manufacturer, when you're getting into these kind of questions, what should I use? Decide together with your manufacturer, and it's going to be a balance between efficiency and cost, of course. When we look at the transformer core, okay, we need to look at this as a two-winding transformer model. So you will have your primary side, and the secondary side. The beauty of this is that from having here some electrical energy, this is being converted into some magnetic energy, and now again this magnetic energy is transformed into electrical energy at the output of this transformer. If we bring this design into a magnetic circuit model, you can see that we have the source here for the primary. We can look at the secondary, look at the signs, plus to minus, minus, plus. And of course, in between, we have the reluctance of the core. In an ideal transformer, we would assume that the reluctance equals 0 or approaches 0. That way we have no losses and we have no magnetizing current to be worried about. As you can see here, okay? So we apply Faraday's law. This is what it gives us, our V1, number of turns, times the variation of flux and time, and voltage in the secondary, again, number of turns in the secondary, times the variation of flux and time. And from here, we obtain the equations for the ideal transformer that are well known. When we go into the real transformer, and we understand that this reluctance of the core, it's not 0, then we understand that there should be some flux times the reluctance that will give you the relation of the number of turns and the currents from the primary and the secondary. From here, you can clearly derive the magnetizing inductance and the magnetizing current for this real transformer. In this case, we can clearly see now that voltage is directly related to the inductance, magnetizing inductance, and the magnetizing current. You can see it clearly here. If the number of turns of the primary times the primary current, let me show you here, go in this direction, right? Plus the number of turns and secondary current, which will be coming from here. If those two add 0, then the magnetizing current is 0, and there is no net magnetization of the core, because they're opposite directions. When the core saturates, the magnetizing current becomes large, and the impedance of the magnetizing inductance becomes small. And this is what you have to remember. Now is when we start getting excited about what is happening with the flux density, because the flux density now becomes large, and the core saturates. And we need to look at the voltage magnitude and the frequency, because really the applied volt seconds are becoming here too large. So we're going to do a little bit of transformer core saturation experimental work. And for this, we have selected an object. This is a Westinghouse transformer, 1970. This is the 1 MVA transformer. And you can see here, originally, When it was fully demagnetized, we moved from operation for a few days, no residual magnetization whatsoever. You can see that the excitation current test, high voltage excitation current test, we made it at 7 kV. And from 7 kV, you can clearly see excitation current for phase A, phase B, and phase C. One thing that I would like you to remember is that one of the important things you have to take into account is that the values that you see on the external legs or external limbs of a core type transformer should be very similar. That's what we call the symmetrical phases inside the transformer. Anyhow, as you can see here, these two numbers are very close. The error between those two is below the 2%. Let's see how do we saturate the core. And the first example that we were talking is, let's do some overvoltage at line frequency. Oops. Okay, we're back. Let's look at this first case. We are applying, you can see here, 60 Hertz, and we start cranking up the voltage. So here is your frequency, and here is the voltage. We're increasing the voltage up to 500 volts. Please confirm on your Q&A panel if you're seeing the changes on the wave responses. I want to show you here that the red wave, the red sinusoidal that you see there, is the voltage, the excitation voltage that we're applying to the transformer, and the white sinusoidal corresponds to the current that is being measured. Right now we're on 5 kV. Six kV. And you can see the sinusoidal is still there. There's no deformation, there's no deviation. We're already on 8 kV, and you can see already that there's a little deviation already on the peak of the wave. We're getting close to 9 kV. Okay, and you can see even better now the effect of changing the magnitude. What we're doing right now is we're providing an overvoltage excitation to the transformer, and that's creating that effect. And now we're just cranking down the voltage. Okay, so as you could see in this first example, I just wanted to show you a little bit how the saturation current will look like, and what is the effect when we keep the same frequency, but we are changing just the magnitude of the response. What we will see on the next one what's going to happen here is that using the power factor test set, the Delta 4000 instrument, I was able to apply different frequencies to the same specimen. In this case, you can see that we're applying 120 hertz. We're already at 3 kV. Again, the red sinusoidal corresponds to voltage, the white sinusoidal corresponds to current. 6.5 kV, 7 kV, 8.5 kV, 9 kV, 10 kV. As you could see here, applying 120 hertz didn't create any deformation of the magnetizing current. Even though you could see at 60 hertz, we did have a deviation already around 8 kV. When we're doing 180 hertz, same thing, we didn't see any effect going up to 10 kV. And now, we will drop the frequency, and we will apply only 45 hertz. kV, 5 kV, and you already see that there's a deviation on the current. 7 kV, 8 kV, 9, 10. So you could clearly see that when we are reducing the frequency, the effect, of course, then let's look at the volt seconds curve. You can see clearly here that applying 120 hertz, we didn't reach saturation at 10 kV. When we're applying 60 hertz, we start getting saturation, or the knee point of saturation was somewhere on the neighborhood of the 8.5 to 9 kV. When we were on 50 hertz for a design that is for 60 hertz, you can clearly see here that we got into saturation somewhere around 7 kV. And when we went on 45 hertz, you can see that we were in the range of the 6 kV. One of the questions that sometimes we used to do on training is, would you be able to use a 50 hertz design on a 60 hertz system, and vice versa? Would you be able to use a 60 hertz design on a 50 hertz system? So as you can see here, there is an influence on the volt seconds, and you really need to remember what voltage is going to be applied. One of the things that you will see on a 50 hertz transformer is that typically they will use a bigger cross section for the core in order to maintain the same voltage and kind of similar properties. Anyway, now we go to the effect of saturation.
Before we move on, I have a couple of questions from the audience. So you were talking about the non-oriented versus grain-oriented electrical steels. Is there a difference in applications of these? Are there any industry preferences between these for transformer cores?
That's a very good question. Typically, the non-oriented magnetic materials or electrical steels are used for rotating machinery, where you don't need the orientation of the flux path. That's not the main important in this case. And you will use the grain-oriented electrical steel, especially for the transformer manufacturing processes. That is the difference here. Okay. Any other question you have?
Not at the moment.
Okay. So let's look at the effect of saturation of the transformer core. Now that we understand the physics behind saturation, and we understand how the system behaves, how the current behaves, how everything is moving inside our transformer, what kind of deformations we can see. And one of the things that you were able to see right now is that the current that we just created here is like a harmonic component. It's a completely distorted line. When we're talking about saturation, a transformer under saturation, the worst case for inrush currents is when the core has residual flux and the switching occurs at the instant of voltage zero crossing with a polarity that increases the flux in the core. So one thing you have to remember, inrush current does happen when you're energizing your transformer. That is part of the system you will have when you are switching on or switching off your system. There will be some DC that will affect your system and will leave some residual magnetization. And normally during operation, on and off transformers on a normal day, that's part of the process, and many people goes without any problem. But it may happen that you can face this kind of condition when you're switching at the voltage zero crossing with a polarity that increases the flux in the core, and that will create a very high inrush current. And for most of the time, it may trip your protection system. The other case is when you're doing some AC testing, where you're using alternate current testing, that could be also affected by saturation of the core. You have excitation current test and sweep frequency response analysis in the open circuit mode. Those are being affected by changes in the magnetizing impedance of the core. And these can create some erratic interpretation of the results, and people may get confused about whether there's a problem in the core of the transformer, whether there's a problem in the transformer itself, or it's just an issue with the magnetization, with residual magnetization in the transformer. So talking a little bit about the inrush currents, as I was telling you, these can have a very disruptive effect, right? Voltage sags, pole stripping of the protective devices, and of course mechanical stress in the transformer winding. Every time we apply a high current, it's not only an electrical stress, it's also a mechanical stress. Of course, the transformers by itself have been designed to tolerate big mechanical stresses, right? But we need to take into account how many times are we going to be stressing our transformer with this possible big inrush currents. And as I said before, the inrush currents emerge when the transformer is energized. The magnitude of the inrush current depends not only on the residual flux in the core, and you have to remember this. We cannot measure how much residual flux we have in the core when we are trying to bring the unit back into service, right? It's also the phase angle of the applied voltage. It's also the resistance of the windings and the saturation inductance. So it's the construction, it's the overall set making the transformer what makes this bigger or less. You can see clearly here the inrush current and the effects of residual flux, the way that Sigre 568 is showing. As you can see, you may have here your normal system, the dotted line, you have your voltage, right? With your nominal current. But if you have a DC offset here, just look at the DC offset here, and the way that is now reflected on the current. Of course, if we now look at the effect between current and time, you will see this damping wave reflecting the flux linkage on the current. One of the things that is important to mention as well is when we're looking at into the inrush current, right? And we look into the harmonic components in that inrush current, the dominant harmonic will be the second harmonic. You can see here on this chart, also taken from Sigre 568, all the components of the inrush current. And as I said already, the main component is your second harmonic. And let's talk about the saturation effect on the testing procedures. We're looking into the effect that will have into operational activities due to inrush currents increase. And now let's look into the testing procedures where we are more involved. C57-152 That is the standard that was published in 2013 to replace the previous standard that we have, IEEE 62, for testing oil immersed power and distribution transformers. Now we have on the section 7.2.7.4, demagnetization after winding resistance measurement. So we have direct current that is being used to measure the winding resistance in order to magnetize the core. When we're magnetizing the core, we are canceling the flux variation of the rate of change of flux. And that way, we're able to measure only the resistive part and not the reactive components of the system. What is it saying here is to help reduce damage to the transformer and associated protection system, or maybe demagnetize the prior to applying full alternating current AC voltage. Then we have in C57152 again, 7.2.11.1.1, the effect of residual magnetism on excitation current measurement. So again, one of the things that we have to remember is excitation current test together with power factor testing is one of the fundamental routine testing procedures that we have in the field. So anything that we can do to improve the quality of the results, to have a better interpretation of the results, should be taken into account. In this case, it's telling you that if you're going to run a test on excitation current, it's better to have previously demagnetized the core. And one of the other things that it's saying is it is recommended that the DC measurements of the winding resistance be performed after the excitation current test. Now we go to the standard for sweep frequency response analysis, C57149, and of course, SIGRE 342. And the most important thing that you have to remember for sweep frequency response analysis is that this is a comparative test. You need to be able to repeat the same condition testing as it was tested before, or the way you have your previous, your original signature of the transformer. So when we look at this, the influence of the residual magnetism may have an influence on the trace comparison. When you're looking at the open circuit mode of testing, and you go from the very low frequencies, which is around 10 or 20 hertz, and you go up around 2 kilohertz, maximum 5 kilohertz, you will see that in this frequency band, there is an influence of the core, there is an influence of the magnetizing impedance of the transformer. You can see here two signatures, one taken without residual flux, which is the blue one here, and the other one with residual flux. As you can see here, up to about this area here. You can see that this is the influence of the magnetizing effect on the response of your SFRA. So, as a comparative method, deviations from the original signature of the transformer might be considered as the failure condition. The first resonance point, and this is important for you to remember, the first resonance point observed in the frequency band from 20 Hz to 1 kHz is the response of a parallel RLC circuit resonance, which is also known as a current resonance and also known as anti-resonance. Deviations in resonance points are one of the first indicators of mechanical deformation of the transformer. Every time you're doing an SFRA test, be careful obtaining your first or your maxima on your resonances, and all the information has to be available for you. If you are acquiring a transformer, if you're buying it from a manufacturer, please request the information to be electronic, okay? Many times people come to us and says, guys, can you help me with the interpretation of these results? Of course we can. So this is what I measured today. Perfect. What is your original reading? And when we look into the original files, they're giving us some PDF files, and it's so difficult to try to compare against just a PDF. So any test equipment that you use, it doesn't matter. Request your manufacturer to use, to provide you with the electronic files. So anytime you can use that information and do an electronic analysis of the data from the manufacturing process and later the test that you are performing in the field. So we know that there's an effect of this magnetization of these residuals.
Oh, dear. Just can we take a couple of questions before we move on?
Absolutely.
All right. So why do we need to use DC during a winding resistance test?
Okay. The reason of using DC for winding resistance testing is because we need to saturate the core. If we were trying to use in the field, let's think about this in the field. We were looking into the procedures, right? So just imagine that you have a 138 kV to 34.5 on the secondary. That means that you need to overcome the nominal rated voltage of that transformer to put that into saturation with an AC supply. Okay? Anything below that is not going to saturate the core. Remember about this volt seconds effect. Okay? You can use a very low frequency, right? And the lower the frequency, then the effect will be there. So the idea of using DC is because this way you will cancel, right? You will apply this signal, and this way you will cancel the inductive component that you have on your transformer. So this LDI over DT will be canceled. There's not going to be any additional change in the current going on the reactive component, and the only thing that you're measuring now is the current times resistance. So you apply DC current, right? And you measure the voltage drop through that coil, and that will be your winding resistance value. That's the reason why we use DC.
Okay, and Mike wants to know what is the effect of magnetization on the excitation current test?
Okay, interesting question. Well, one of the things that you have to remember, guys, is that when the system has been magnetized, right, what you will see when you're running your excitation current is an increase of your excitation current values. Now, one more thing that you have to remember. The excitation current is directly related to the voltage that you apply for excitation. Some of the problems that we have seen in the field is many people will test, for example, using the TTR, the turn ratio instrument, and they will get an excitation current value, which is very low because the voltage that you're applying here is in the range of the 40 volt to 100 volts. And then somebody is testing the transformer again using the power factor high voltage piece of equipment, and they are testing the transformer at 10 kV, and they get a completely different number, right? And they get scared because now it's several times more, right? And they miss that part, that the excitation voltage is directly related to your excitation current. Now, if you were testing with the same voltage once, and then later during your routine testing, you're testing that with the same voltage your transformer, and you see that there are discrepancies, you will see that if the core was magnetized, you will have an increase on your excitation current. Something else that you will find is that you normally will compare the symmetrical phases. As I was telling you, the external legs on a core type transformer are symmetrical because the length that we have for the flux path is the same, basically, right, as compared to the central leg in your transformer. So these two external legs, your phase A and phase C, maybe, those two will have a very similar value of the excitation current. One of the things that the standard is recommending is if you see that there is a discrepancy between those two values greater than 10%, it might be magnetized. So before you judge the transformer saying that there is a problem in the core or there's a problem with the windings, let's try to demagnetize it first and run the test again. Okay?
Okay, sounds good. So we'll leave the questions for the end of the presentation. And we can go on. Thanks.
All right. So let's look at the solution here. Let's look into the transformer demagnetization process itself. So we were saying to demagnetize the transformer cores, there are several ways. One is the variable voltage constant frequency, what we call the VVCF source. Then we have constant voltage variable frequency, the CVVF. And then we have decreasing the amplitude of an alternating DC current. And this sounds a little bit contradictory, alternating DC current. And we will explain that a little bit later now. But you can see here what we're trying to do. Basically, if we were applying AC, what we're doing is going from positive to negative, and we're trying to minimize the effect of the saturation. As you can see, the hysteresis here has to be reduced. The bigger the area that we have inside our hysteresis, the higher the losses that we have, the hysteresis losses that we have in the core. So we're trying to minimize that. By doing this variation of the magnitude of voltage, we're applying AC, and we're changing the magnitude, and we're decreasing it down to a value very close to 0 volts, then you will see that this effect is basically accomplished as shown in this graphic. This is just the generic algorithm that we use for DC demagnetization. What are we trying to do here? We will select the input parameters. What is my input parameter? How much current did I apply for my winding resistance testing? Let's say I applied 10 amps. Okay, so if you were able to saturate the core of your transformer with 10 amps, then you should be able to demagnetize the core with the same 10 amps. So we select, for example, the 10 amps for our start current, and we start creating an interval, say 80%. So we start injecting maybe a positive 10 amp, then we discharge, and then we charge the transformer to a negative 10 amp. So this is what we are talking about, an alternate DC current. So we go from positive to negative, and then back to positive, and then back to negative, and we keep changing the values on several steps of about 80%. And this is being repeated on many cycles until it's ready. So for a case study, so you can see this better, we're going to go back to our Westinghouse transformer. And you can see the first thing that I want you to see is what is the response of this transformer without the effect of saturation. You can clearly see here the symmetrical phases. You can see here symmetrical phases go basically one on top of the other. So very similar responses. And the non-symmetrical phase, as you can see here. And of course, we can clearly see where the first resonance, or what we call here, is the parallel resonance, or the current resonance, or the anti-resonance, is being shown. In this case, it's around minus 90 decibels. And this is for the low voltage winding. Again, a very symmetrical response. You can see here what you have for the low voltage symmetrical and the non-symmetrical phase. Now, we will saturate the core by static winding resistance measurement. So basically what we did is we saturated the core, we did our static winding resistance measurement, right? And we measured the resistance on every single coil of my transformer. And now you can clearly see the discrepancies that we got. To make a little bit more clear for you and to expand a little bit the visual effect, you can see now that the frequency response here, it's not on the logarithmic scale, but on the linear scale. And we're looking only between the 20 hertz and the 2 kilohertz, where is the influence of the magnetic core of the transformer. What's happening now? First of all, if you look at the original signature that we had, the symmetrical phases, now the response is not symmetrical between those two. So that is the first clue. You're testing phase A, you're testing phase C, and now those two don't look symmetrical. The other one, you will clearly see that there is an impedance deviation here, and you will see also that the first resonance on the non-symmetrical phase, in this case that we can clearly see, there is a frequency shift, right? But the magnitude is about the same. In this case, you can see here that the magnitude is about the same, right? But there is a frequency shift for those. What has happened? Of course, the magnetizing impedance of this transformer, the magnetizing inductance has been modified in this case. So now we're demagnetizing, and we are demagnetizing the transformer, applying this algorithm only to the central phase, to the B phase, which shares mutual flux with both legs of the transformer in a similar distance, in a similar path. As you can see here, now that we have demagnetized the system, you see that it looks very symmetrical again. It's just overlapping one to the other, the responses. Same thing here for the non-symmetrical. But let's look into it a little bit more in detail. Okay. So now you can see here that, yes, it's very, very close. When we demagnetize only the central leg of the transformer, we're getting almost the same response. There's a little bit here, anyway, of a deviation. I hope you can see what I'm circling right now, because this is a little bit interesting now when we're talking about the split frequency response and the open circuit. Everybody expects it to be just one on top of the other. There might be something else that we need to take into account. Same thing here. When we look at the response of the symmetrical phases, it's almost overlapping one on top of the other, but there's a little tiny deviation. Let's look for a second at the process itself. So when we decide to demagnetize, and we're going to look at all windings. So this is a typical procedure. We're not looking now at demagnetizing only the central phase. We're looking now at demagnetizing or run the process of demagnetization on all the phases of the high voltage side of the transformer. As you can see here, we started with, it's a process of 60 cycles in this case. The current that we're applying goes from -10 amp. I just reduced some of the steps here so it's not so boring for you guys. But you can clearly see here, we are going between H1 and H3. We went from -10 amps all the way down. We're going to 0.001, so 1 milliamp on this alternating DC injection. From here, we move to the next phase. Again, what is important in this process when you are demagnetizing all the phases? You need to remember which orientation you are giving to the magnetic domains of the transformer. You want to move in the same direction. You want to keep everything oriented in one single path. So you are not going opposite direction, moving your domains on one side to the other. And now you can see here, you have your H2 to H1. It's almost done. So it's a charging process and a discharging process. Positive, negative impulses. And then we go for the last phase from H3, H2. As you can see here, it's going from the high current of 10 amp to very, very small values of current to get as close as possible to 0. You can see here the process is almost complete. Okay, and now we have the unit fully demagnetized. So if you see here, now that we have demagnetized the system, spending 3 times the time that we needed only for one single intermediate leg of the transformer, and we're looking at all the high voltage windings, you can see on the response that we're getting, those are more or less the same, right? It's overlapping one on top of the other for the symmetrical phases, and it looks like overlapping perfectly also on the non-symmetrical phase. Let's look at this in more detail. And we come back here, and we can see a little deviation now. For the symmetrical phases. And look what happened on the non-symmetrical phase. So now is on the same frequency with a minimum deviation in magnitude, but you're getting the same resonance point. One of the things that is interesting here is you can see that the first resonance is getting close to a minus 100 decibels. And that is kind of typical on many transformers. So what is the conclusion here, guys? And this is where we're gonna close this webinar, and we're gonna get a little bit more questions from you guys. Demagnetization of power transformers in the field is practical using the DC method of alternating pulses. You don't need to bring a huge power source to demagnetize a big power transformer with AC. That's going to be very expensive, heavy, and not really practical. So it's much easier just to go with a simple DC power source, right? And especially the equipment that is being used for winding resistance measurement is the same equipment that counts with the demagnetizing process or demagnetizing feature. The approaches to demagnetize the transformer might be different. Only one phase or all phases. As you could see, the effect of each individual approach might be different depending on the type, size, construction of the transformer, etc., etc. But one thing is clear: there is no 100% full demagnetization. There might be a little bit of a difference. There might be a little bit of discrepancy, and that is because just imagine that you are applying a force. This excitation voltage that is being applied, this current that is being created on the coil, right, is creating this magnetic field, and everything is moving, and your magnetic domains are going to one direction to the other direction. And now you saturated the core of this transformer with DC, and you put it on one side. In order to get those domains in a different direction, or to get back into the original position where they were at, it may take more than just all this process here. It might be a little bit difficult to do that. And there's a concept also related to this, which is the viscosity of the magnetic material. And so never expect to have a 100% exact demagnetization process and get exactly the same response. As you could see, if you are running your test, you demagnetize, you get basically the same response. You visualize it as the same. If you go into the little bit of a microscopic analysis and you start looking into more detail, then you will see that there are these little magnitude or frequency deviations that are really not affecting at all your analysis. So the idea is to show you that the deviations observed must be understood by SFRA users, not to confuse with potential problems in the core of the transformer. And the algorithm indeed cancels the residual magnetism in the core and minimizes the stress during re-energization of the transformer, not increasing the magnitude of the inrush currents. And this is what you're trying to prevent, right? You're trying to minimize any mechanical and electrical stress on your transformer. Trying to extend the service life of your transformer. Just so you know, for Megger, our new product is the MTO250, which is capable of testing transformers up to 1000 MVA for winding resistance measurement, static winding resistance measurement. It's a DC test current up to 50 amp. It has the integrated demagnetization feature. It validates proper operation of on-load touch changers. It's field portable and is computer controlled with internal data storage. Also, we have the MTO300 series. The beauty of this device that it's one connection, and then you just press once on the bottom to run the test, and it has all the windings, all the coils being tested. It has simultaneous winding magnetization. It has test operation of on-load touch changers, built-in auto demagnetization feature, and it has automatic discharge. And of course, saturation, transformers. We cannot forget about the instrument transformers. And when you are testing CTs, one of the things that you have to do is also now, and if you follow the standard C5713.1, you need to run winding resistance testing. You need to run saturation test or excitation current test. You need to run ratio tests. In order to do that, one of the best pieces of equipment that we have available is the MRCT. And the MRCT is a simultaneous multi-tap measurement which reduces testing from 20 to 40% of the time when you are testing a multi-tap CT. It has integrated single-phase relay test systems, has built-in demagnetization feature as well. So this unit will also demagnetize your CTs. Will measure all ratios and saturation curves on multi-tap CTs with one lead connection, and it has a built-in insulation resistance testing. So that's all that we have today for this webinar and this presentation. Do we have any more questions here from the audience?
Yes, we actually have quite a lot of questions, but we'll try to go through a few, and then if we don't get your question in time, we'll answer it offline with you. So you can continue typing in the questions, and I will ask Diego some of the questions few I've asked earlier. So Mark asks, they've had SFRA results where the first resonance shows some sort of noise response and cannot be visualized. Do you have any advice on how to deal with an issue like this?
Okay, one of the things that you have to remember is, again, the importance of looking at resonance value. Some equipment, different manufacturers, different dynamic ranges on the SFRA test equipment. If your transformer, for example, is below the minus 100 decibels for the first resonance, most of the testing equipment for SFRA will not see it because it's hitting the noise floor of the instrument itself. It has nothing to do with the noise of the substation or anything like that. Megger instrumentation is designed for testing below 130 decibels. We haven't seen responses below that value, but yes, we have seen a lot of responses in the range of the minus 100 decibels, minus 110. So make sure that the device that you're using, the instrument that you're using, has the dynamic range capable for testing within those ranges for the magnitude of the SFRA response. Otherwise, what you're looking at is the noise from the instrument. Okay, is the floor noise of the instrument, of the electronics of the instrument. It has nothing to do with your transformer.
Okay, let's have one more question, and we really have to wrap it up. So when we demagnetize a transformer, is the AC method better or the DC method better?
Interesting question. Both are good, but the AC in the field might not be practical, right? You may not have enough power to do the AC. As I was showing you here, it's volt seconds, right? So when you're doing the AC, you really need to reach not only the nominal voltage of your transformer, but beyond that to get into saturation, right? And then you need to demagnetize, so you need to go up and down and bring it all to very, very low voltage magnitude. So you're looking at a very big power source on your AC. Whether with a DC, you can get into the same demagnetization process with a portable unit that is, easy to carry around in your substation. So it's really easier to go with DC in this case. I would prefer to go DC, but both systems, if you're looking just at effectiveness of the methods, both are effective.
Okay, so we are, I guess, a couple of minutes over our time, and if we didn't get to your questions, don't worry, we'll follow up with you individually via email after the webinar. So we'll email you a copy of this presentation in the next few days, and the recording of the session will also be available on our website within 2 weeks of the webinar. When we close the webinar, you'll be redirected to a survey. We would really appreciate your feedback so that we can continue to improve future webinar sessions. Thank you all for attending, and have a great weekend. Thank you, Diego.
Thank you very much to all. Thank you, here.